Welcome everyone. We are here to talk today about introducing IEEE, the 1800.2 specification. This is entitled The Next Steps of UVM, and I'm very proud to start off the discussion here in this tutorial session. The focus today is going to be me first to kind of give you an introduction to the efforts that we've done over the last year and a half for UVM and getting it to the IEEE level. But the majority of the time we're going to hand off and give it to Sri, who's going to talk about all of the changes that we put into the IEEE and then what's going to be in the standard. And then after that we've got a tutorial session, and then we'll have a use case scenario of UVM. It's going to be demoed to us today as well. Today, my part here, we're going to talk briefly about the history of the 1800.2, talk about why standardization was necessary for a methodology. And then I'm going to highlight the milestones we went through, and then give you an introduction into how UVM is being managed today. We have this interesting dynamic between the Accellera body, the working group, and now the IEEE, who owns the specification. And so I want to talk briefly about what that means with this dual ownership and who owns what part of UVM. And then we'll talk about what's happening right now. I'll briefly talk about some of the changes you'll see in UVM, very high level. And then after that, we'll talk about what's going on right now with IEEE. Like, what's their current status? What is Accellera doing with the standard that's been picked up by the IEEE? And then we'll do some introductions for the rest of the material that we'll present today. If we have enough time, we'll start to answer questions about backward compatibility as we raise the issues with relation to that. So this is just a standard foil here on standardization. Why was standardization needed? BIP, we've seen it grow exponentially in the industry from the days when we had VMM and OVM and ERM and all the different incantations the vendors supported for verification IP. So we finally pushed 8 years ago to have it evolve and merge into a universal verification methodology. And really, the core of this, right, is that the industry benefits from this tremendously. We just couldn't afford the significant amount of time and energy and effort consumed converting from one form of VIP to another. And so that was the reason UVM came about. It was to enable the industry to save on reuse and effort on conversion between the different standards. So that's UVM. And of course, we've seen the verification libraries evolve over time with all the different components and aspects of the language. So this is just showing you a brief history where we have all these different verification libraries and methodologies based on system Verilog, and then the evolution over time to UVM that we have now. So Accellera, we've been working on UVM for, like I said, 8 years. We started off with the 1.0 standard. We actually had an EA before that. And then we've had 2 major releases since then. For every major release, by the way, those are the spec releases that were officially released by Accellera. But the 1.0 and the 1.1 releases that we had an associated implementation release with it, meaning we actually provided a base class library. And then with those releases, we had a bunch of bug fix iterations. So if you recall, we had 1.1a, 1.1b, 1.1c. Right, these were iterations and releases that we made to resolve issues that came up that were filed as part of that specification, as part of the issues that needed to be resolved in the actual implementation of the spec. And then, August of 2015, we finally had a part that was submitted for IEEE. It was accepted by DASC in that summer of 2015. And we have worked on that committee. Was a year and a half of effort where we brought together all the companies that were participating in Accellera, plus a number of others, to help us to improve the IEEE version and specification for finally getting it released as an IEEE spec. So the good news here, obviously, is that standard was finally finished late last year. It took us thank you. Yes, it's finally released, and as of 2 weeks ago, the SAASB board, approved it. So it's a very, very significant milestone. So it is now approved as an IEEE standard, and the actual spec should come out in the March timeframe. The editors are working right now behind the scenes to clean up all of the language, any language issues. Just, it's basically just in the hands of the editors now to get it up to snuff for release. And the other highlight there is no other verification methodology in the IEEE. This is the first one. UVM is going to be around for a very long time. This is definitely the first incantation. We'll talk about next steps here in a minute, but this is a very significant milestone. And this is just showing you the history of the milestones that we've gone through, highlighting down here in green the fact that we now do have a IEEE spec. This is 1800.2. It says February, that's when it was approved, so it's going to be released here in the March timeframe. And everyone also is curious about who owns what. When we started having these discussions 2 years ago, 2+ years ago, about what to do with UVM specification and the implementation, these were all discussions we had from within Accellera. So we tried to figure out, through the many discussions we had, who's going to own the specification long term. And there were a lot of working group members that said, no, look, Accellera needs to own it. They need to drive it up to the IEEE. And IEEE is just a blessing ratification body. And that seemed to be kind of the prevailing point of view at the time, that really Accellera would still drive the specification, we'd get it to the IEEE, clean it up, bless it. And that would be kind of an ongoing circular process every 3 or 4 years. And it seemed to make sense. Once we started the IEEE effort, though, it was interesting because the majority, if not all of the working group members at Accellera came and joined us in the IEEE committee. And we had more people that joined us. I think we added probably about 4 or 5 major companies when we started working on the IEEE spec. And they all had a lot of great input. In fact, what we ended up doing is realizing that even though we had put a lot of work into cleaning up the spec prior to contributing it to the IEEE, once it landed on the IEEE side and we started looking at it in depth again, we realized, oh wow, there's a whole bunch more things that we need to focus on. More accessors to add, more APIs to remove that really weren't visible or needed in terms of end users being able to see them in the spec. And so it evolved into more work that got done on the IEEE side. And because we saw members in that committee that were in Accellera, the whole question came up again about who's going to own the spec, right? And so we had those discussions again at the IEEE level. And the bottom line was, okay, let's just break this out for now. Let's make the IEEE as the owners of the specification, the LRM spec. And let's just have Accellera own the implementation, okay? And everyone was there from Accellera as well, and so it seemed to make sense at the time. That's really kind of where it ended. There's still more discussion. In fact, we've had more feedback from the System C committee as well, saying that's not going to be your ideal state. You're going to have to go through some pain as you do your implementation to try to match it against the IEEE. And you'll see that there is some balance there that has to be struck between the specification ownership completely being on the IEEE side and not vetting it first through some implementation, okay? And because that was the learning they told us. They said it helped the System C community a lot to actually do some kind of testing on the spec through their implementation, right, on the side before they actually read that up into a full spec of changes that got put and introduced at the IEEE level. Okay, so there were those discussions that we had as well. There's going to be some learning as we progress, but currently the vision is that IEEE will own the UVM specification. The implementation will be owned by the Accellera committee. If you're wanting to contribute, and I highly recommend that, we've got a lot of contributors that are coming in that I haven't seen before. We kicked off the Accellera group here not too long ago, once the IEEE work was done. But if you're willing and able to come and help with that effort, highly encourage that. We are seeing a lot of people that are there to help. There's a lot of enthusiasm for it. And there is a lot of work that has to happen in that Accellera working group body. But as I said, it's going to be interesting. I'm sure we'll learn as we go here in terms of changes that we implement in the implementation that we may see as needing some adjustments on the spec side. So we are still learning, is my point. So this just highlights basically a summary of what I just said. IEEE will own the 1800 spec. It will produce the LRM that allows for multiple implementations. Accellera will own the actual base class library, and they will provide the initial release of the IEEE compatible base class library. I'm not going to say when. That working group just started back in December. I'll go more in depth about what's going on there. I don't have all the details, but I know that they're working on producing a schedule. So they're working on a schedule to get a first version of UVM out that is IEEE compliant. And I'll just leave it at that. Now, what I see happening in that committee, by the way, is once a version comes out that's IEEE compliant, they're most likely going to rev on that to add additional stages of making it compliant or backward compatible in such a way. I think Sri will go into some detail with that. And we'll also be revving on bug fixes. That's kind of the vision that I heard discussed there as well. So we know when a first revision comes out, it's going to be buggy. We're going to have early adopters that are going to test it. There's going to be some revisions, bugs that'll get filed, things that we'll have to fix. We'll have a Rev B, a Rev C in order to fix those issues. So what's changed? When we started working on this direction of going into the IEEE, one of the big things that got raised in the committee was, okay, if we're going to go to the IEEE, do we really need 500, 600 pages of a specification? Is there something we can do to clean it up? So when we started having those those deep discussions, we realized there were a lot of, if you know the history of UVM, right, the specification that was created was done through automated utilities that would extract the information from the actual library, the actual implementation. And so because of that, a lot of things got in there that really didn't need to be there in terms of a full specification. A lot of like APIs that only the writers of the library cared about, of the actual implementation that we were releasing. So we decided, okay, let's just get rid of those. We don't need, they're not APIs that the end users need, okay? They're just APIs that are there because we use them internally as part of the implementation. So one of the big first efforts we made before we contributed the specification from Accellera to IEEE was to remove those non-user APIs, okay? So there's a lot of work, several months of effort that went into finding out which ones were there, going through and writing utilities that would remove them automatically in the base class library to see if anyone broke when they were gone, right? So there was some churn trying to get the specification upgraded, but upgraded meaning pulling things out that we didn't think were needed there. The premise being we were trying to start with a skeleton UVM specification that the IEEE could use, and then if we needed to build on it later, right? We didn't have all this junk that was there, that was legacy that no one used, right? We wanted to start with a cleaner slate and then build on it after that. So that was the premise, the thought process that went into what we did initially. So a lot of APIs were dropped. These were non-user APIs. They were only used by the base class library. So we said, let's get rid of them. There were other non-standard APIs. Example, reference APIs that we just didn't really see were needed by the standard. So we got rid of a number of those, and there's some examples up here. And then we started looking at what needed to be added, right? We saw, for example, a number of properties, right, inside the classes of the base class library that were global. They could be changed by end users. They were accessible. And we thought, okay, well, that's not a good thing. So we added a bunch of new accessors in the form of new methods for those classes to access the data, and we removed access to the data directly, right? So things that you would normally clean up in a better implementation of a base class library, right? We went through and upgraded those as well. So those accessors make it so that we can access the data without directly accessing the data properties. Some examples here, again, UVM init, UVM run test, callback, etc. We also focused our effort on cleaning up, and one of the other big asks, by the way, when we started our IEEE effort was, if you're taking it to IEEE, can you please look at the other IEEE standards that are out there that are being used as part of your UVM base class library and clean things up. You've got TLM, that's a specification that's out by System C. We do use our own version of TLM inside of UVM. And so there was some work, some effort that went into attempting. I'm not going to say we made this just work, but we made the effort of looking at the TLM, how we implemented it in UVM, and seeing if there's any way we could reconcile that against the System C version of TLM. Okay, and in the end, we'll talk about that more in this presentation. But in the end, we realized it was going to take us, probably a year of effort at least to go through and really upgrade that to be at a level where everyone was happy with the cross-pollination of TLM from System C and how we use it in UVM. And so there were some minor cleanup things that we did, but we really didn't come to that level of being synergistic with what System C has. There was some effort as well into registers. Can we clean up the registers? Can we make it more in line with a lot of the other standards that are out there? There was some effort that went into that as well. We also did some user guide material removal. These are examples or methodologies where in the specification and releases that we had in the past, they were just there as part of the code, but they didn't really add a significant value. And so we went through and cleaned up a lot of the user examples as well. The user guide's not part of the spec. And then really we were looking at ambiguities in the specification as well, right? Focused in on, with the language that we use in the specification, is there anything that's not clear? Can we clean this up? So just overall reading through the specification multiple times, try to see if we understood it. Did it make sense? From one part of the specification to a different clause, do these APIs make sense? Are we defining these all correctly, right? So there's a lot of work that went into actually removing and clarifying ambiguities. And so all of the work that went into creating the IEEE that got approved late last year, there was a lot of voting and balloting and just normal processes to go through to actually get everything approved. That actually took about 4 or 5 months of effort. But in the end, we got everything ratified as of February of this year. And now we're looking back at Accellera. We reformed Accellera back in December, the UVM working group there. And now we're talking about what are the steps now that we need to go through to create a new base class library that matches against the IEEE spec. So discussions that we're having, the biggest one that took us probably a couple months here to deep dive on was how do we approach backward compatibility. So there's been a number of discussions about the approach. How much do we carve out in terms of first release of UVM that's IEEE compliant, and how much backward compatibility is there versus second release, or what kind of switches we use to enable backward compatibility. So if you can imagine, if you've ever been in a backward compatibility discussion, it gets very deep. People are concerned, right, about their current code base and whether or not it's going to be a significant turn or significant changes are going to happen in order to make them compliant against IEEE. Well, all of these deep dive discussions were happening at the first part of this year. And so the Accellera effort, as is outlined here, will ultimately determine what types of changes do you, the end user, need to make to ensure backward compatibility? What is the overall guidance? What does need to change? Once you make the changes with the IP, what are the implications for you? Can you use this in the old environment? And does it have to be used with a new UVM IEEE accept, right? So the question really is like, if you have your current implementation, right, how much change is going to happen for you guys in order to upgrade it to IEEE levels? And again, as I mentioned before, there's no timelines yet, but that group is there. They're meeting every Thursday, 9 o'clock Pacific time. It's every Thursday. It's a 2-hour call. If you guys are interested in joining that effort, I do highly encourage you to join. Again, you have to be an Accellera member. The website was accellera.org/join. If you're interested in joining, all the information is there. And as I mentioned, IEEE 1800 done, the work is done. And really the bottom line now for that effort is we're stopping. IEEE is done as far as we're concerned for the spec being produced this year. We're going to wait probably at least about a year or so before we dive into having any discussions on spec changes, because we want to give time now for the Accellera working group. Remember, these are all the same people, right? We want to give them the time that they need to start fleshing out all the deltas that happen. What do we change? And how does that impact the base class library, right? So that effort is going to take us a year minimum to get an IEEE version out that is compliant against the IEEE. And again, I mentioned this big topic, right? IEEE and backward compatibility. There are a lot of really good opinions and a lot of good people pushing, and I've been involved in most of these discussions. I'm actually pretty happy with the way that they're going. You know, when we look at trying to make upgrades to a spec, one of your biggest concerns is maintaining backward compatibility. And if you can't maintain backward compatibility, okay, and we've done this in the past, provide utilities that allow people to take their existing code base and run the utility on it to get it up to spec as far as you can, right? And if you can't get all the way, then document the rest of the things that we know of that are required in order to take that code base and port it over to the new version of the implementation. And so all of those things are being deeply thought through. The issues are, we broke them out into 5 different categories, basically consisting of these questions here. I'm actually going to hold off and let Sri deep dive on them, give you the introduction into the different options we're looking at to maintain backward compatibility.
Hi everybody, my name is Srivatsa Vasudevan. I work for Synopsys Inc. I plan to go over the changes between the UVM 1.2 release and the upcoming 1800 spec. Before we get into this discussion, I want to emphasize that we've spent a lot of time on taking a good hard look at UVM 1.2 and trying to understand for ourselves which pieces of this are standard worthy and which pieces actually could use a little bit of enhancement. And we went down this path for each API that we found in the library, and we also went through each of the other APIs that were not exactly documented, that probably needed to be documented because there were guys out there who were using them in the first place. So there are several aspects to the changes that you will see. When you look at the IEEE document that comes out in about a month, it's going to look like the UVM class reference manual, fundamentally, okay? The class reference manual, I would say, was prettier because it had colors on it, but this one is at least all black and white. But, okay? So, but the thing is that it has a listing of classes, how they're expected to behave, methods, what are the user APIs in those methods, and what are the behavior of those methods. And that is what is documented in the IEEE document. So the Accellera version here was actually used as a starting point for that document before that document came into existence. So we're going to talk a little bit about a number of things here. The first thing I'm going to do is highlight the 1800.2 enhancements over UVM 1.2. As I go through this presentation, you're going to be able to see that 1800.2 is fundamentally an enhanced version of UVM 1.2. I hope to convince you that if you have huge backward compatibility concerns, I want to reassure you that we have taken a great deal of care. A lot of thought has gone into the committee in order to making sure that the thing is compatible. Nobody likes to have a lot of broken code. I'm an engineer myself, just like all of you, and I don't want to be maintaining it if I could be doing something better. So I'm going to go over that. There are a few enhancements which are key in a number of major areas, and they're listed here. So there's a big introduction in terms of policy classes for the common operations that you see. There are some significant changes as far as the factory itself is concerned. And I'm sure that these changes are going to excite you because you'll suddenly find out that there are things that you could never do before that you can do today. We had some feedback on some behavior of the components. So we made a couple of small enhancements there. Callbacks is another area where we have spent a little bit of time and energy based on the feedback that we got from various groups before we got into the committee. And then there are some minor enhancements and changes. I know that there might be a lot of material to go through as we do this presentation. I hope to make this a working session per se, in the sense that when you leave here, you have a clear sense of what UVM 1.2 to IEEE changes were. And I hope you'll realize by the time me and Mark are done that the upcoming standard that's coming up would actually be something that is a lot more easier to use for all of you and much more intuitive than UVM 1.2 would ever have been. New people coming into this standard will say, aha, this looks exactly like I've dealt with in other languages. And we have attempted to give that look and feel while maintaining the backward compatibility. So let me now get a little bit into the UVM working group effort per se. As I have just said, we are making an effort to ensure backward compatibility. one of the key efforts that we are doing is to make sure that this library is going to be around for a very long time. So we have tried to make the library easy to use, intuitive, easy to maintain and enhance. So a guiding principle here has been that instead of having fields and assigning values to them, we have provided accessor methods. For example, you will remember the printer knobs. It would be printer.printernobs.some value. Okay, and it looks very different when you're looking at the printer knobs versus you looking at a compare or whatever. It looks quite different. So what we've done is we've uniformly provided accessor methods across all of these classes. The other thing we've done is we've removed the implementation artifacts so that if we release future versions of UVM from the working group, that they don't remain overly constrained. And I'm going to talk a little bit more in detail, because what you'll do is you'll see that I actually will call out explicitly what are the changes that have been made between the two releases. We've tried to make this library a lot more flexible than it ever has been. And there is now no need to use macros in order to get some functionality. All of the methods that were actually called within the macros are now completely documented in the LRM. Another key feature that we've had is that a number of classes that were there in UVM 1.2 were not factory enabled because registration wasn't there, the various factors. We've gone ahead and cleaned up all of them. So it's a uniform treatment throughout the library. As a result of all of this, the API is now a lot more uniform than it ever has been. A number of people were using some of the methods by looking up the source code and realizing what some of the methods did. And what we've done is we have now provided a documented API for each of the classes and methods. Some of these things were actually present in UVM 1.2, but they were not in the documentation. Some of you have looked through the documentation, you will see a nodocs tag or other tags, but then you were able to figure out what it was doing, and some of you have used it in your own things. So all of this is now documented. Whatever we've realized has now been documented because it's a user API in the IEEE. And so one of the big benefits from this is, since you've got an LRM, anybody can build a UVM library if you choose to. Okay, as long as it sticks to the spec, you got something that's IEEE compliant. That's the beauty of it. Maybe you can build a far more optimized one, but anybody can build it using the API that is provided. There are no secret sauce methods. Everything uses the documented API that is now in the LRM. One very, very big feature that I want to bring to everybody's notice is that you will see that debug hooks are not mentioned in the IEEE LRM. A lot of you are using it. I'll give you a good example of what a debug hook is. For example, a factory.print or some of the config.db resource trace or phase trace. They are not mentioned in the LRM. That doesn't mean that cause for the removal. The concept behind removing all of these debug hooks is it may be possible for others, vendors or anybody to provide far more efficient hooks. I'll give you a good example. If you've done a UVM config.db trace, you will remember, you get a huge listing and then you have to pair up the two of them. It's a bit of work. Some graphical tools are able to pair them up and say, hey, look, the set happened here. This is where the get happened. And especially if you are trying to figure out, okay, fine, like my simulation was stuck in a certain phase, there may be a far better way of getting to know why that is happening. So what we've done is, I'll talk about that. Please don't be alarmed that it's gone and therefore I can't use it anymore. That is not the intention. The key point here is that the hooks are not mentioned in the LRM. That's about it. They're just not mentioned there because there may be better ways to do the same thing. Okay, and I'll talk about what's in the Accellera implementation for a minute. Now that we've had that background, let's talk a little bit about what's in the reference implementation. We are working closely with a number of people in order to produce a reference implementation from the working group. It will contain the UVM IEEE API with the classes and methods that are defined in the LRM. But the important thing to note is it will contain additional useful APIs that are not part of the 1800.2. And the reason being, we found them useful, but we also thought that maybe they are not standard worthy at the same time. So there will be additional useful API. And I think many of you are familiar with the UVM node deprecated switch, which used to allow you to turn on code that was deprecated in 1.2. The new reference implementation that is coming out is going to remove all the code that was deprecated by 1.2. So you will have 1.2 to IEEE would be one level of deprecation, the subsequent level is removed. This is something you have to remember. Maybe vendors will provide you with the integrated library, but that is not the scope of the working group. Accellera working group will not provide you with a compliance checker or things like that. Our job is we're going to produce, as a group, we're going to produce a reference implementation. Users can use linting or other solutions to make sure that their code is compliant to the 1.2 API. And there are a number of solutions to this problem. Maybe we can have a separate discussion about this. As Tom has mentioned, if you feel strongly about it, please become an Accellera member. Please join, please give us your ideas, and please help us implement it. The most important thing here is we're going to do our hardest. We're going to try very, very hard to keep existing code from breaking. Okay? Unless it's absolutely impossible, we're going to try extremely hard to keep your code from breaking. So far in the last 40 minutes, we've been talking about this. Now I'm going to go into the details. I've structured this presentation in a way so that when you look at the 1800.2 LRM, and then you look at the UVM class reference manual, you're going to find one which is several hundred pages, another one which is several hundred pages. You're going to wonder, oh my God, where am I going to start and where am I going to stop? What the heck changed? How am I going to find it? Okay. What I've done is I've basically extracted those two. Okay. Fundamentally done a diff, don't ask me how. Got a lot of help from a lot of people. But fundamentally what we've done is we've extracted out each of the APIs that has changed, that impact you. And those are the ones we put into this presentation. Please forgive me if I missed a couple. I'm human too. So the first icon here is a thing that looks like a document. So usually if you see this icon anywhere in the presentation, it would be a method that was actually present in 1.2 that we forgot to document in 1.2, but it's made its way into the IEEE LRM. Often was an internal function, but then now it's got promoted to being a public API because some people are using it. So don't think that it's a brand new thing that got introduced in UVM. It probably was already there for the most part. If it is brand new, I'll be talking about it in a bit. This fork in the road kind of thing is an important aspect that I want to talk to you here about. This is fundamentally saying that UVM 1.2 was going in a certain direction, and the approach taken by the IEEE group was slightly different. Okay, it's like a fork, like you're taking a different path in the road. It does not mean that it is backward incompatible. Most often it's backward compatible too. But, it's a philosophical difference. And then you'll see a hand with an icon finger pointing on some lines on some slides. And I try to put these together so that you are aware if you are migrating from 1.2 to IEEE, these are the places you should be looking at. Okay? These are the kinds of things that will trip you up. Okay? This new cloud little thing, I couldn't find a better icon. It says it's new in 1.2. There are a number of 4-state to 2-state changes in the IEEE, so I've basically done that. Most of the simulators should swallow it. There should be no problem. But if you look at the two signatures, you're going to go, hey, wait a minute, what happened? You're going to see that. So now that we have these icons, hopefully you'll remember there's a fork in the road, a finger pointing, saying please watch it, look for this, a cloudy thing that tells you, hey, look, okay, this is new, okay, and a 4-state to 2-state. Other than that, there's the little document. Everybody knows documents. So I'm now going to get into one of the most important changes that we see as far as UVM goes. This is one of the more fundamental ones. If you guys have used compare, print, copy, record, you would have noticed that each one of them had a little bit of a different feeling in the pre-IEEE days. What you would have seen is that a copy is a direct assignment, and sometimes it calls a method. The printer had a printer knobs thing dangling at the end of it. The comparer had some variables that you had to set. A recorder was its own thing. So first thing we wanted to do is we realized that there are several of these operations that are common. And guess what? As people create derivatives of this environment going forward, they basically want the same kind of behavior to be applied across these objects. They want some sense of uniformity. So what we've done is we've created this concept of a policy class. This policy class, every operation, copy, compare, print, pack, and record, now uses a policy class. It creates a uniformity across all the operations. So there's a base class here. It's a base class for all policies called UVM policy. And this is different. This is a new class you'll see introduced. And I'm going to be highlighting these sorts of things as we go along. And this is a change. As you can see, this is a change from the way we used to do it in 1.2. Okay, earlier you will notice that you had printer, comparer, packer, recorder, all as standalone classes. 1800.2 now changes them. So you've got UVM policy being used as the base, virtual class printer, comparer, packer, recorder. These classes now extend from UVM policy. Okay, and there are a number of capabilities being given to the base class per se. These classes have concept of a state. The class is also factory enabled. What does this mean? In the middle of a simulation or somewhere in the beginning, you guys can go do things with it. This is kind of opened up. Earlier you had a do copy, do compare sort of thing. and you were stuck with those, right? And suddenly you decided, hey, look, I got these new pieces and I want to go make recursion capabilities. You couldn't do that. Today you can, okay, with the new version. So the other thing about this is that it extends from UVM object. I'll be talking about UVM object in a minute, but what I want to hammer down is that all classes extending from UVM object are factory enabled. So there's a generic mechanism, extension mechanism. If you guys remember the TLM2 type of extension mechanism, a similar mechanism allowing user to pass additional information to the policy, and you can use it to alter the interactions of the object with the policy. You know, you may use an extension to selectively filter some fields or methods. You can just apply a different policy to change how an object is, you know, printed, compared, etc. And therefore, what happens is that you can have several of these policy objects living in the simulation. Just apply the current policy at a certain time. I'll give you an example of how that's done. And what will happen is that, you know, you fundamentally can just change the behavior at that point. There are a number of new accessor methods which I just listed here. But fundamentally, you know, these things allow you to get the object, get the extension, figure out, oh, I'm operating, you know, since it's a common class, I'm operating on a printer or a comparer or whatever, and then take the appropriate action. So you can have different actions happening to different things. This might not sound like much. One thing that will happen is that a lot of it will probably, you'll get a default implementation along with the working group because you need that for the library to operate. But you're going to, you know, this will be one of the basic changes that you'll see. Okay, so the whole summary here is that, you know, this class is there, it allows you to tailor capabilities. Now let's go into what the packer does. The packer has another change as well. If you remember, the packer used to add a null terminating byte to the bit stream after packing strings. After packing strings, you know, after packing objects, we had that thing in order for the unpacker to realize what was going on. You could not do this in UVM 1.2. You could not use a bit streaming operator, okay? The requirement was to allow both the packer and the unpacker, you know, as long as they understand each other, it should be okay. And this is, as you can see, this logo, you know, is fundamentally a philosophical difference. Earlier, you had to have things a certain way. And as a result, what we've done is use metadata is not mentioned in the LRM, okay? As long as you have a packer and unpacker that understand each other, okay, you could have one on system Verilog, one in C, or vice versa. As long as you've written those two compatibly, it should work. Okay, let's go to copy. Copy's gotten a little more interesting than it should be. We've been doing copying from day one. Copy did not have a concept of a policy before. It was this one standalone class that was sitting there by itself. So the signature of copy has changed. It now has an additional default. Okay, so this your existing code should compile. Copier extends from UVM policy and gives you ability to control recursion state within the copier. You can apply different recursion policies by setting the default copier. And then there are a few methods here saying, you know, set this guy as the default, set this recursion policy as a default, you copy this object for me, etc. And what I have not mentioned so far here is there is a enum type which tells you whether it's UVM deep, UVM shallow. If you guys remember, in the older versions of the LRM, you had UVM deep, UVM shallow, but some of them were not really working very well. You know, it was very hard to get that stuff working. In this case, what happens is that, you know, you can have something that actually does something meaningful with it, rather than relying on any macros. The other important thing here is that it's extensible. So I'll give you an example of what that copy thing looks like. You know, I just talked about it a little bit in abstract terms. This is an older example. What I've done is, you'll see that this is to the older way of doing it where you had to assign something. So what you'll see is, I have two coding styles, the 1.2 coding style and the new way of doing things. And what I've highlighted in that little box, so you'll see that I had the older way of doing things here. And what I just wanted to do is just, you know, put a box around it just to illustrate that the way of doing it is a little bit different, in the sense that you basically get the active policy into your do copy method, and then you can use the copier in order to apply a certain policy to it. The other thing here is that you can add extensions to this thing. You couldn't do that before. So you've fundamentally gotten an additional back hook in addition to the do copy hook, wherein you can go do stuff with it. And you can apply that uniformly across all objects. And you can do some selective filtering. Let's go into comparer. So if you guys remember the comparer, Tom earlier had talked about accessor methods. Again, you're going to see a little bit of an icon there. I put this icon everywhere where I saw the UVM policy, because I just wanted you guys to be cognizant of the fact that, hey, look, something has changed here. Okay. And UVM 1.2 allowed you to set the comparator variables directly. In addition to that, we now provide you accessor methods. It's sitting as a layer on top. The big thing here is I think that it makes it much easier to use. You don't have to exactly remember which knobs are in the comparator. If you're using a good IDE, chances are the IDE may be able to give you a listing of methods too. So let's take a quick look. There are a few additional methods here, and I think if you look at the UVM 1.2 version, if you had a custom comparator, you'll notice that in UVM 1.2 you would have directly assigned the variable. In this case, what happens is that you've got a set show max. Okay, so you've got a set get kind of methodology here, and as a result, each of the variables got an accessor method. And so if you look at other languages, you'll find that, hey, look, this looks pretty natural. Remember that in addition to this thing now extends from UVM policy. Okay, so the same thing, all the things that I told you earlier about you being able to go and do other things with it are there. So that is why I call this as you getting a bit of a boost. We can now uniformly apply this across all the objects. Okay, so printer is another place where there's fundamentally a very big change. Can you guys remember all the knobs? I don't think so. I can't. Okay, so one thing we've done is we've created a base class for all the printer types. This base class also extends from UVM policy. So the same stuff that I gave you in the policy works, but it allows you to set the default printer, and all of this is done by methods. Okay, earlier in pre 1.2, you will notice that the printer could be set to null. You could very clearly set it to null. And some simulators would be very happy, they'd quietly go along and you'd wonder why nothing is happening. The LRM in this case is very, very specific. You cannot set the printer to null. This is a change from 1.2. The other thing that we did is that we took all the UVM printer knobs. If you remember looking at the printer knobs, they were an aggregation, or maybe the right word is an amalgamation of every possible knob for every type of printer into that one class. And it was dangling off on the side. So what we've done is that we have merged the functionality from the printer knobs into the printer base class. Okay, it will be backward compatible, but the settings that are relevant to each printer are now moved to that specific derived class. So it looks different. This one will look a little bit different. What happens is that you'll have a bunch of methods, but since the subsequent classes, as you're going to see, derive from UVM printer, all you're going to do is you're going to see the accessors. But then there's a layer sitting on top of it. The key thing about this is that it's uniform. It looks very much like the others, and it's easy to use. It makes it a whole lot easier to use. If you think about it, you say, okay, I'm dealing with all printers. Guess what? I need to set it in the base. You can set it in the policy. This thing is factory extensible. So you can just set it in one place and you can do things with it. The knobs have been broken up. The knobs are broken up into settings that are in each of the relevant printers. That's the change that you'll see. A number of these methods are now part of the UVM printer class. And there are accessor methods for setting each of these knobs, and that's the listing that you have here. These are new. So basically you'll see begin elements, default radix, end elements. If you remember logging it to a file, you have set file. I'll talk about UVM file in a minute, that's changed a little bit, but you basically see a bunch of set get kind of methods. And it makes it uniform. So if you look at the comparator has the same thing, the copier has the same thing. You look at the recorder, packer, everything, every one of them is the same. It looks uniform across all the classes. So let's talk about the line printer. The whole reason I brought up this and a few of the others is just to highlight the fact that there are 3 or 4 methods here that are relevant to the line printer. The rest of the stuff is actually in the base class. These are the settings from the printer knobs that were actually relevant to the line printer. So these got pulled in here. So corresponding for the tree printer and the other printer that I'm going to throw up these examples, you'll notice that what I did is if I wanted to set the default earlier, I had an equal to, here I basically call a method. Okay, that's fundamentally the difference. And I've highlighted it in bold so that you can see it. My thing to this is that it makes it a whole lot easier to use and customize. The table printer has the corresponding the same thing. I'm going to go fairly quickly over the next couple of slides. But basically, it's a similar concept here. You can set a default, you can set the indent, get the indent, do things with it. And this would now only be relevant to the table printer. You don't have to remember all of these. And if you have all of these common things set in a common class, and then had that being a part of the library, you would have a consistent look and feel across all your simulations. This makes it easy to use. The same is true with the tree printer. It's got get set separators, and basically, it's the same sort of thing. Recorder has some changes. Recorder actually has 4-state to 2-state changes, and you basically see that it was an int to integer. And that is integer, it was int. So it goes from 4-state to 2-state changes. Most simulators should swallow it. I don't see this as being a big backward compatibility thing, but that's the first occurrence of the finger icon. Okay, that's the first occurrence. I think you're going to see much more examples where it's far more relevant. But this is just a very, very simple minor change. And an example of this kind of change is there everywhere in the LRM where we saw int. So here's the essential operation summary. What I did not gloss over, I'll go over right now. We've considered backward compatibility extensively while going through all of the policy classes, which have gone through a fairly significant revamp. For uniformity purposes, accessors are provided for each of the settings that are there in each of the things. All classes now use a policy. You cannot set policy classes to null. That's the big deviation from earlier behavior, okay? You'll notice that why there for that reason. There is a default to ensure as much backward compatibility as we possibly can do it, and you can make changes in flight during a simulation. Things are not hard-coded, okay? There are a few additional methods to help people. The packer has a reset, wherein you find that the state of the packer is confused or you're trying to do something with it. You've taken some number of bytes and you decide, I'm going to chop this thing in half. Printer has a flush, saying, okay, fine, like I want to flush everything. Comparer also has a flush additional method. And UVM recorder has a new free method. Each of the field macros, I don't know how many of you guys have gone into the UVM internals per se. They had a bunch of methods, okay? And they were all secret sauce in the LRM. They now use methods that are now documented in the LRM. Other key thing you'll notice is UVM flags are documented. They were not, and it's a type. This is a big change if you guys want to watch for it. But there is UVM flags is now a type. It's an enum type. Wherever we saw magic numbers and integers, we've gone and replaced them with types. So UVM flags is a type. Okay, so here's where fun starts with the UVM factory. Earlier, if you remember, the factory, when you made a call to the factory called new under the hood. You couldn't register abstract objects. So we've gotten two new types of classes to support this functionality called abstract object registry and abstract component registry. This allows you to register abstract component types with the factory so that you could derive them later and do things with it. This is just a little bit of a tack on additional functionality that you did not have before. I think it was requested by a couple of companies, that if I remember correctly. So this just got added. I don't know if you would be needing it, but fundamentally remember that the behavior is slightly different because of the new operator under the hood. Implicitly, when you do a create, it will call new. Okay. With these cases, it will not call new because these are abstract. So we've added a couple of methods to it. There is an aliasing wherein you have one type name and you can alias it to another type name. And then you have one type which can be aliased to another type for instances and for types. One important thing here is, again, this is the first occurrence of that document icon. See, it had its way of showing up. But basically, there were several methods people were using that were not part of the LRM. These are now documented. So if you see these, please don't be alarmed. This is also a place where we want to talk about big changes. There were many classes in UVM were not factory enabled. This was a shortcoming. A lot of us saw it as a shortcoming. All classes, I repeat, all classes derived from UVM object are factory enabled by default, unless otherwise mentioned in the LRM. So the big thing that you have to notice is that since many more objects are now registered in the factory, if you remember the factory.print 012 that Srini and us had given in the last year's DVCon, wherein we talked about how to debug the factory. The point here is that there are a lot more classes now registered in the factory. And as a result, what will happen is that when you look at the listing, you're going to see a lot more classes. And this is something you'll be wondering, oh my God, what is going on? The key thing here is that every object coming from UVM object is factory enabled. That basically means you can go take it, extend it, do things with it that you could not do before. So the other thing is that it has an ability to have abstract classes and an additional API. Let's talk about UVM component. If you remember, during the build phase, we had a method called apply config settings being called. What this would do is it would basically go out and call and try to get values from the config DB, and there was no way to turn it off. Especially when you had components where there were a large number of settings. We have seen significant slowdowns at several places in the build phase, and there was no way to turn it off. So one thing we've done is that we've left the default in place, but we've introduced a brand new method called use automatic config. And the default implementation returns 1, okay, to leave backward compatibility in place. But if you want to shut it off for a particular component, when you derive the class, have that method return a 0. What it will do is it will not call apply config settings during the build phase. What this does is it has an effect of speeding up your build times. At the starting point of the simulation, when the build phase is happening, if you had like maybe 30, 40 variables, I've seen up to 200 in one or two places. And you see that, it's taking a huge chunk of time. This is one thing that you can use in certain components. Let's go to UVM object. UVM object, if you remember, we talked about all these policies. The compare copy, again, that is compare, it should have been record, but that's a copy paste line from an older slide, but forgive me for that. But fundamentally, they have different policies in place. And there are a couple new methods for seeding, and these are introduced to ensure random stability. All objects are enabled by default. Okay. The key thing you have to remember is that all of these methods get default policies by default. When the library comes up for the first time, UVM init runs. You're going to see the factory and all the other objects, command line processor and other things getting created. Default policies are kicked in place for you. You don't have to do a thing. Okay. But at a later point in time, once the components are all built and you cross the build phase, maybe you want to go change a few things here and there. You want to do something, you can do it. This is an easy slide. As far as I'm concerned, this is the slide that requires the least amount of explanation because it's just going from 4 state to 2 state. It talks about integer being int to integer. Now coming to omissions. Some of these items were considered not standard worthy. So the UVM comparators are omitted from 1800.2. They may be present in the Accellera implementation per se, but we haven't found a lot of people using these extensively. They've been omitted from the standard. There's a little bit of change when it comes to reporting. I've highlighted it in bold. Errors are now reported independent of verbosity. That's a fundamental change. You might see earlier cases versus now. You'll see a little bit of a difference. Where did this error come from? It was actually a bug in 1.2. So we just cleaned that up. So one important thing, this is a little bit important, okay? UVM action now was an int, and now it's of a type, okay? Some simulators are going to swallow it, but if you've seen this set severity action and these methods, these things now take an enum type. So it's enumerated, so you can do a dot name and you can do things with it, okay? Earlier, what's my magic number? And then somebody redefined it. There's no way on earth you guys would have been able to find. This goes back to the question about whether it would have been debuggable. Because remember now that, by far and large, as we've cleaned out the LRM, we've gone and replaced these magic int numbers with enums. We've done that. So if you are a little bit suspicious, hey, wait a minute, what am I getting here? You can do a dot name or something, print it out and see, oh, okay, this is what I got. And if it didn't match your expectations, that's a quick debug right there. Okay, report server. This was a fairly simple one. It should be completely backward compatible, but file was set to 0. But then file is equal to std out, and basically these things have been enumerated because we didn't want magic numbers in the LRM. So eCatch for the report catcher. If you guys remember extending the report catcher, eCatch now returns an enum, not an int from 1.2. This is another philosophical difference that we've had. And one thing you'll notice is that you'll have to actually take account of the enum. Most simulators, I'm told, will actually swallow it nicely and completely. You shouldn't see a difference, but it returns an enum, not an int. You might get a warning from some simulators. One important thing I want to do is tell you that there was a number of debug features, especially when it comes to the report catcher itself. It has not been mentioned in the LRM. There are some methods that have been actually taken out. And so we will provide a compatible implementation, but then anybody can add their own extensions to this as they see it fit. So here's the fun part. You remember there are various places where we had callbacks in 1.2, okay? Each of them was their own standalone class. One thing we did is we went and created uniformity out of everything. And so UVM callback now extends from UVM object. And if you guys were paying attention to me in the beginning, UVM object is factory extensible, which basically makes this guy also have the same thing. Okay. These are parameterized, so there'll be different types. But fundamentally what happens is that, you can go and now do things with callbacks that you never could do before. The other thing is that they're uniform. So what has happened is, as a result of that uniformity, the callback iterator that was different now is kind of unified, right? And so that has now been documented in the LRM. So you can actually go get a list of these things, see what it was, see which ones are enabled, things like that. This is where I think we made your lives easier. There were many do macros in UVM 1.2, many of them. Okay, so the UVM do macro is now redefined so that it's got a couple of defaults. You got one macro to remember. This is the one that is documented, the rest of them aren't. Okay, you want to use the others, they probably will still work. But this same one fundamentally morphs into the others if you've looked at the code. So it's only one of them. Only the tick UVM do macro is there. The typical start methods and the other fun stuff that you used to use is still there. Nothing has gone away. Nothing's gone away. But the thing is, this has a couple of defaults. This is easy to use. So the working group's reference implementation will contain additional API that I did not talk about. For example, the phase trace, config.db trace, resource.db trace, then the factory print methods, the audit for some of the classes, Callbacks had some additional audit functions. Those are all considered debug hooks. They are not core to the main part of the simulation, but they are there in the reference implementation provided by Accellera. Okay, the Accellera implementation, when you get it, it will contain additional useful APIs that makes your life easier. And if there is a better way to implement something, we will, trust me, we are going to explore that. And what we're going to do is we're going to try to make it easy to use. One thing is any pre-1.2 UVM code that is deprecated is going to get removed. So please plan on it. If you're planning to move to the IEEE version, you have a couple of choices. One is you can go straight from 1.1D and make the jump to the IEEE 1. I don't believe the changes are significant. I do not believe they are very significant. However, if you want to go to 1.2, put a toe in the waters, check it out, you're welcome to do that. But the important thing is that the reference implementation that's provided by Accellera will remove pre-1.2 code. And any code that causes a semantic challenge between the IEEE and the UVM 1.2 basically means that the IEEE 1 wins. This is something to notice. If there is code that has conflicting definitions between 1.2 and the IEEE 1, the reference implementation will give you the other one under a switch, but basically the IEEE 1 wins. And that'll be the default.
So I'm going to talk about two topics that are also affected by this IEEE change, TLM and the register library that are part of UVM. So just a quick reminder of what the TLM stuff is. So it's a transaction level modeling library that's in UVM, that's implemented in System Verilog. It's a collection of interfaces and channels that are used for communicating transactions, moving things at the transaction level. And it's based on the IEEE 1666 System C TLM standard, although it doesn't exactly implement that. I'll talk more about that in just a second. So when we started talking about this is the list of Mantis items that were filed. I'm not going to go through this list. If you're in the mood and you're interested, you can go look up these Mantis items and get all the gory details about what happened. The main point is there's not a lot, right? There's just a dozen or so items that we looked at in deciding what we wanted to do with the TLM as far as the IEEE standard goes. One of the first topics that came up is the consistency with System C standard. What should we do there? One is semantics of System C, and the other is trying to deal with language issues. So System Verilog and C++ are different languages, and fundamentally they don't fit together. So we decided to not break backward compatibility. So we're going to keep things as much the same as we can. There was some naming issues also that came up. So, for example, there's NB put in the System C standard, and there's try put in the UVM. Should we change try put to NB put and vice versa? So we decided to keep the names as they are because it would break backward compatibility to change it from try put to NB put, and we didn't see any real value in doing that. There wasn't any new capability. If we were going to break backward compatibility, there'd have to be a real reason to do that, and this didn't seem like a strong enough reason to break backward compatibility just to simply match names, particularly since the names don't ever occur in the same space, right? They're not in the same namespace, so there's no conflict at all. It's just slightly annoying, but it doesn't hurt anything. Then we looked at the whole thing about TLM itself, and we decided that we're never going to actually match System C TLM. And so we're not going to necessarily try. Well, I shouldn't say it that way. We're going to try and move it as close as we can, but we're never going to get there. And it would be a very bad thing to have two things called TLM that were IEEE standards. So to have something called TLM in the 1800.2 spec and something called TLM in the 1666 spec would not be a good thing. So we decided what we're going to do is we're going to change the name to UVM TLM, and we're going to then wave our hands and say, okay, they're not the same thing anymore. I think this is a good thing. This kind of gives everybody a little bit of a break, but that doesn't mean we're going to ignore the System C stuff. We're going to maintain the provenance and maintain and keep it as close as we can, but we don't require now to keep them exactly the same because it turns out it's not actually possible to do so for differences in the language. So I'll give you an example just real quickly. For example, in the generic payload extensions in System C, use partial template specialization to identify the extensions. You can't do that in System Verilog. So there's an example of there's a way that System C and System Verilog will never be exactly the same, and the semantics will be never exactly the same. So why try and kill ourselves here? That's about it with the TLM stuff. In registers, there was a working group that formed, the UVM register working group. They had a lot of discussions and talked about the current limitations and things that needed to be addressed with registers to kind of fluff it up a little bit. They looked at a couple of issues, missing capabilities, and also system-level dynamic addressing kinds of things. The original intent was to try and align with IPExact as other standards, but mainly it was IPExact, and then generally improve the documentation. And also the idea was to make backward compatibility. So this is a kind of a theme throughout the whole thing, with the exceptions that Sri mentioned earlier. In the end, there was no really major changes that affected backward compatibility. So this is good news for everyone using the register facility. The LRM documentation was changed. We did address the system-level dynamic use model issue, which I'll talk about in the next slide. And they decided that the alignment with IPExact would be deferred. It was really just ran out of time is what it boiled down to. To deal with dynamic register models, now you can unlock a model. So previously, when you created your register map, you locked it and then it was done, and that was it. Now you can unlock it and make changes and relock it. So this allows you to model dynamic hardware. The other big change was just, again, kind of a cleanup, was to take various base classes and make them factory enabled. So these now, formerly these were all virtual classes. They're not virtual classes anymore. They're regular classes. And they have the UVM object utils macro added, so now they can be used in the factory. So all these things that previously were not able to be used in the factory are now factory enabled.
This is an application of UVM. The UVM for RTL Designers is just that. And it's something that we've encouraged here on the Accellera Tutorial Day, is to have companies that have applications for Accellera standards to come up and present. So we did want to mention that it's not endorsed by Accellera. This is an application, and it's a use of UVM itself. There are others. Mentor has one. Doulos also has a UVM for designers, and these are examples. But I do want you to take a look at this. It should be an interesting presentation of UVM for design.
My name is Srinivasan. I belong to this company called VerifWorks, which is based in Bangalore, India. Myself and Krishna would share this presentation. This is roughly the agenda, as Adam just rightly put. This is not truly endorsed by Accellera, and it's just a website that we have called gotouvm.org. I have the link coming down some slides down the line. And basically, it's an open source layer that we developed for some customers. And I felt it's the right time. It's at a level that it could be wider deployed and adopted. So it's just a way of presenting it to you that, hey, here is how we have found some of our customers use the UVM in an easier way. And today's target is RTL Designers. I know there are not many of them perhaps here, but some of you probably work with your RTL Designers and then want to share some of what they do versus what you do with them. And it's also always a challenge to get them into UVM. And we're going to show you a couple of quick ways. And as it goes with quick, it's going to be dirty. Some of them are going to be dirty, and I'm going to make it explicit right up front. Some of them are really Q&D kind of a solution, wherein we want to get the RTL designers to start looking at UVM very early in their process. So we have a couple of slides, one of them borrowed from our friends at Mentor Graphics. We would quickly show you you would know this anyway, the journey. And then I would briefly give you a couple of slides to say what we have actually done with the GoToUVM. It's not just a code generator. It does have an app that would generate some structure for you, like the drivers, the sequencer, the monitor. It's a template generator. There is one part of it. But the major part of it is actually an API layer that we have added on top of UVM. And we also have a new thing called a signal access, which lets you and your RTL designers to create quickly a corner case to do a force, deposit, release. And I'll briefly mention why this was needed. The bulk of the presentation should focus on the register verification, which would be handled by Krishna as well. And then I also have this waves to UVM. I believe the order is slightly reversed, but you would see that. And we would conclude with how do we bridge the RTL designers UVM, or the so-called GoToUVM, into a full-fledged DV. This definitely comes from friends at Mentor Graphics, and I explicitly obtained a permission to say, okay, I could share this over here. And some of you might have seen it, and then I believe there is an updated version of this slide coming up tomorrow sometime. Harry Foster would be presenting this. So essentially what we are trying to say here is UVM has been phenomenal growth that we have seen between 2012 and 2014. And it's done by a group called Wilson. That's all I had there. Now, for most of you here who are kind of UVM experts, you see this, you figure it out. Yes, it's here, there is a UVM object, there is a UVM object, and then there are these different base classes derived from it. Beautiful. Now, you try and show this to an RTL engineer, he or she gets totally upset. Hey, this is too complicated for me. I am a Verilog VSDL engineer, and don't put me all this OOP into me, virtual classes, factories, and etc. It just gets too much for them. So we want to find a way wherein we could show them a simple UVM to start using. So a typical structure, again, this is coming from one of the tools without naming them, but it's a nice, I would say, a schematic of a typical UVM bench, wherein you have a desktop and then an ENV and then one or multiple agents. And then each agent contains a driver, a sequencer, a monitor, and perhaps a scoreboard and few more things. And that talks to the DAT. Now, the point is, a DV engineer is very familiar with this. They easily can create this. But what about the RTL guys who have a slightly different requirement set, which I'm going to talk briefly and then go into it. The mechanics of UVM, again, a lot of you are familiar with it, so I'm going to leverage on that. But at a very high level, we have a series of components like the drivers, the monitors, the sequencers, the agents, and etc. And they all get hierarchically hooked up using the component : new. And again, for OOP aware engineer, the double colon and then the new is not really a strange thing. But you try and show it to a Verilog or a VSDL engineer, again, I'm not demeaning them, it's just that they are busy with their own stuff. And you try and show them the concept of a parent class, which is not really an OOP parent, but is a test bench parent per se, and then try and tell them, hook them up rightly in this particular shape, it gets harder for them. And we also have macros. In UVM, the phasing is a very important part, wherein the reset phase, the main phase, if you decide to use them, or the run phase, right? And the objection mechanism is a must in UVM, even to get a very, very simple, if you want to write, let's say, clock 1, I want to drive a signal, and then clock 2, I want to drive another signal, you must have an objection, otherwise the whole thing ends at time 0. So again, a lot of it is familiar to all the UVM aware engineers. Now, we need to simplify this because as we go with them, again, if I were to derive from during the lunch, there was a nice panel, and then they talked about how do we go to a mass deployment onto an UVM. So the reason is that not every engineer is familiar with UVM. And RTL designers require very simple tests to write because they want to hand off a quality RTL to the DV engineer than to find low-hanging fruits. They want to find those themselves. And today they write their own VSTL or a Verilog bench, but rather can we have them write UVM? Some of the requirements, typical ones, they simply want to write few tests to wiggle the wires. Sometimes they want to do a forced release. Again, I'll give you a couple of cases where we have seen this. Sometimes corner cases, sometimes those so-called safety and security features that, okay, I just want to see a random fault in that particular place. And the register access test, this is really the bulk of this. Again, as I said, Krishna will come and talk in detail about it. This has the context that a lot of these SOCs, the IP that go into SOCs contain registers, and how do we easily verify the registers without learning a lot of UVM? That's kind of the background. And there's also other portion. This is all users are writing the code. Now, there are also auto-generated tests. For instance, you could say, okay, I have a waveform. Can you convert this into a test bench or a test case? That's something I call it a waves to UVM. We'll talk about that. And there are some DFT patterns that you want to send in a UVM framework. So, a couple of slides, I'm going to go a little faster to say that I'll reserve more time for the registers. Anyway, the standard messaging is $display. We all know this, but the good would be to add a file and line number. But very difficult or it's very hard to get every RTL engineer to write a $display like this. Of course, UVM provides a lot more facilities there. There's a tick UVM info with ID, message, and verbosity. Now, it's definitely powerful and versatile. Again, for a UVM aware engineer, this is no brainer. But go and tell it to an RTL engineer, instead of using a $display like this, try and use a UVM like this to tick UVM info. The first thing that comes up is, what am I supposed to do with the ID? Again, I'm writing a throwaway test. Why should I bother so much about the ID? And seasoned users try and use get name, get full name, so on and so forth. So in either case, I believe the IDE is something that we could automate. The verbosity, again, there would be a nice way if you could add default value there. And this goes back to the history of system Verilog language itself. So essentially what we have done, we created a new macro, which is kind of a wrapper around the existing UVM APIs, which is equivalent to with the verbosity having a default value. I kind of asked my EDA friends, why didn't we do it in the UVM itself? We could easily do it. There's a lot of history behind it saying, okay, initial versions of the tools did not support the default value for the macros. So I said, okay, let's create a simple display macro that would create a default verbosity, and then it would be equivalent to saying UVM info with a get name automatically in there. So it gets down to the usage like this. You could do a hello world like this, or I found a match with a UVM hi. Again, this is not added by me, but somehow it came in. And then you can also format it using a S format tag if you want to print address and data. So in this case, it becomes a hi. Otherwise, by default, we default it to a UVM media. So that's kind of the starting into the go to UVM. It's a system Verilog package. It's not just a script. It's not just a Perl script, but it's actually a system Verilog package. There are also Tcl-based and Python-based apps to create the infrastructure needed. And it's a minimal subset as a system Verilog package. It's a subset on top of standard UVM framework. And since it's on top of UVM, if you want to use other features in the UVM, you're welcome to use, because this is not a restrictive new UVM library per se. It's just built on top of it. So it's a simple messaging. The test will be from UVM test, and the phasing is automated. You don't have to worry about this. The objections are also automated, and we also have automated test pause and fail declarations. And for those who have used other methodologies such as VMM, one of the nice things as an engineer I found was when I run the test, it comes up and then tells me the test passed or failed. I may not be able to rely on it completely, but if it says failed, it's failed for sure, right? Now, unfortunately in UVM, we don't have it, and it's not a big thing to add. It's just a small, tiny API. You have to go and say, hey, get the severity count and then add a pass or fail mechanism. We have done that so that people don't have to do it themselves. And it's all open source code. You can download it from a GitHub. So it uses the main phase and the reset phase. User fills the main routine and the reset routine, and reset is kind of optional, but of course it's recommended to fill the reset. And okay, there's a little more detail. I'm not going to go into this pure virtual part, but once you start using it, you'll find it. Okay, good. It internally handles the objections. That's a good thing. So let's take a very simple example and then see how this works. Again, please realize that this is not for those complex use cases. This is for a simple 5/4 design. I have a couple of signals. How do I toggle pins without having to create a transaction model, a driver, a sequencer, an agent, and so on and so forth. That's kind of the idea. So we're going to use the go to UVM test layer. That should hide the complexity for us. Here is the code. Essentially, you import the standard UVM package. We also have our own package called VW go to UVM package. You import it, and then there is a test begin. And this get_wif is nothing but, if you kind of can correlate to config_db, this internally does config_db : get. So we call it a macro, a get_wif, and then there is a task reset, and then there is a task main. This is equivalent to a reset phase. This is equivalent to a main phase. And we straight away toggle the pins using WIF and then a CB as in recommended in a system Verilog code. You say, okay, there is an interface, and then there's a clocking block, and then there's a signal that you go and try. How does it work? Under the hood, again, this is a slide that just tells you, okay, this is the base test that we extend from UVM test, and then we say, okay, inside the main phase, I go and call the main. So user fills the main, and if he or she forgets to fill the main, we would actually throw a compile error because it's declared as a pure virtual. Again, if you have missed certain method, again, this is a good thing about phasing. At the same time, if you miss the phase names or you change the names of the phases, you cannot get the automated phasing in UVM. And to prevent that misuse, we said, okay, let's make it a pure virtual in the base class. So essentially, any test that is derived from here, if he or she does not fill the main, the compiler would throw an error. The top level connectivity is similar to a Verilog flow. So we say, okay, here is the FIFO interface, we instantiate it, and then here is the set_wef. Again, this is our preferred approach of connecting to the UVM. I think there's at least one more thing that I was just reading today on the Verification Horizons newsletter. I'm sure there are 2 or 3 different ways of connecting, but we believe this is kind of the most common approach to say, okay, config_db set, config_db get. Again, without having to expose the whole thing to the end user who is the RTL engineer, we're going to say, okay, use the macro called setWef, and then in the test, do a getWef. So let's look at side by side, how does a Verilog test look versus a UVM test now, or a good UVM test. So essentially, okay, here is a at percentage of clock, we have a at CB. And then we say, okay, load equals 1. I'm going to say vif.cb.load equals 1. Please note that the .cb is a great convention to use. It's not a must, but of course, it's a great convention to use to go through overclocking block. So similarly, okay, you have a load equals 1, counter enable, up down, and then you have the same thing here. So our claim is an engineer can write Verilog, they can now start writing UVM. Now, on top of this, what we have done is, given that RTL designers already have an RTL top, we don't want the engineers to sit and write the interface file and connect to the virtual interface. We have an open source TCL app that actually talks to the EDA tool under the hood and then gets a list of ports and then creates a system Verilog interface. And it works with all tools, I'll list all the tools here. And then given an RTL tab, it generates a system Verilog interface, the package, and the template test. And then it also gives you a makefile. So it's integrated with all the major tools, as I told you, without showing a name of a tool. This is how we integrate it as a menu item. You give me an RTL like a schematic, and then you push a button, you could get the UVM out. So that's something we are trying to integrate to Xilinx as well, so that the FPGA engineers who are kind of new to UVM, if they want to go to UVM, this is a very easy way to do it. So once you have a schematic up, you can imagine that you can query the ports of the RTL, say what are the inputs, what are the outputs, and what is the size. Right? Once you have that information, it's fairly straightforward to create a system Verilog interface. And the code is all exists on the web. So this is the next quick app that I'm going to talk about, which is called the Waves to UVM. So specifications include timing diagram, and it's a formal, unambiguous way to capture timing. It may not be comprehensive, but we do have timing diagrams dealing with digital designs. Now, how about we convert the spec timing diagram into a UVM test? Now that we have a UVM layer, which is a very, very thin layer that says, okay, I can go and toggle the pin right from my test case using a vif.cb, right? Now, can I take it to the next level wherein I have a waveform, can I convert that with a push button, go and give me a UVM test? So it works with all popular waveform formats from different EDA vendors, but since it's an Accellera day and I'm asked to say, okay, does not mention any tool name. So I used the open source one called Wavedrome. Some of you may not be familiar with it. It's not owned by me, it's by someone else. That's wavedrome.com. It's basically a JSON-based description language, and that renders an SVG or a PNG that you could annotate to your documents. Here is how it looks. For example, a simple protocol. I have a bus write read valid and then a write read signal here. This is a text-based description that you could create a waveform, and then of course you can extend. There are lots of details in this, but without getting into all the details, we have a clock. You have a write read valid and then a write read signal. And you push a button called the Go to UVM app, then this code comes out. So what happens here? Again, very similar to what I showed you in the FIFO example. Okay, as per the timing diagram, on the clock 1, the signal is supposed to be X, and this clock 2, the signal is supposed to be 1, and the clock 3, the signal is supposed to be 0. We exactly mimic that, extract this information from this particular specification, and then spit out this code for you automatically. Again, I don't believe anyone will pay for it. So I open source it. I'm not an EDA company per se, so I wish to be, but I know this is not easy to sell. So I said, okay, let's make it open source, put it on the web. To get to the little more detail, each signal will have a similar drive method, and then the task main that we saw in the Go to UVM layer will go and fork off these individual tasks to say, okay, each signal will be mimicking exactly what the spec has. And this has been kind of appreciated by a lot of RTL engineers who are mainly the FPGA users who have a tiny spec and they want to create a quick UVM. This is a very easy way to do it.
Hello, my name is Krishna Thottempudi. I work for Qualcomm, and I'm here to present how to make register verification an easy technique from designer perspective. Already you have gone through the APIs and macros, how a designer can use as a thin test layer from the user perspective without knowing the mundane or complex code which is hidden behind it. I personally like the Waves to UVM, which is very handy technique for the designers. So I'll be going over signal access API with respect to force deposit release. It's a very handy technique and recommended approach to find or create corner case tests by the designers themselves without having to know UVM. Signal access within UVM. So the recommended approach is to add a virtual interface which is difficult for sideband signals, It may not need to work across the HDLs. It's very hard to use for the first timers. So there is a macro or API, which is a base class to wrap those EDA vendor functions. The signal access API in go to UVM. So basically you have the GTU force, deposit, release, static functions, which will be available for you to use. Basically create a corner case test to wiggle the pins and create those early tests and find early bugs before handing off the baseline to the DV guys. So it's pretty much easy to use. It's not a recommended approach, but it's pretty much available for the designers to use in the main function and create those corner case tests with a thin test framework by using the GTU UVM package. So these are the EDA vendors who provide the VPA-like system functions. So I just mentioned about the like Cadence and Mentor and Synopsys. So this is the main topic. So in this context, for example, if you take a fresh protocol interface and there is a design team and there is a DV team and design engineers, everybody start at the same time, but design engineers doesn't need to wait for a DV environment to be created to handle their initial verification for their registers. Generally, the registers and clock control modules are the ones which are initially bought up. So they don't need to wait for the DV engineers to create a environment for them or facilitate them to do their early verification. Instead, they can use this approach, which has the UVM intelligence built into it, and eventually also bridge this and eventually reuse it into the full-fledged DV environment and thus reduce some bandwidth or time effort from DV perspective. Because this approach has the UVM reg model and UVM intelligence behind, where the user or designer doesn't need to know UVM, but he can easily use that UVM intelligence behind this framework. So I'm going to talk about that. So the prerequisites here are the register specification. Obviously, it is available as IP-exact XML format, and nowadays people are with YAML format too. So there is a tool that converts the IP-exact register spec to UVM reg model code. There are some proprietary scripts which are being written within the companies. But there is open source also. So that can be fed to the script, which will convert the reg spec to UVM reg model code, which builds the built-in sequences and it facilitates the environment. So there are two approaches to handle this task. Is the designer knowledgeable in UVM with respect to the VIP they are using? So when I say VIP, it is the behavioral functional model which will be used with respect to their configuration bus protocol interface. So if the designer, let's say that he's not knowledgeable in using that VIP. So we have a simple approach where RTL designers can write a simple way to write register access tests in UVM framework. How to do that we'll go through in the following slides. They just need to fill in the GTU write and GTU read tasks in the interface, in the system verilog interface, which is like a module and module is like interface and interface, where we have set of signals, we have the clocking block, we have which specifies the BFM clocking block and monitor clocking block, and you can fill in the write and read tasks to create the write and read access tests basically. So if the designer has some preliminary knowledge of UVM and he knows how to use the VIP, you can explore the VIP potential on that particular configuration bus protocol. When I say configuration bus protocol, each core can have its own configuration. It can go through SPI protocol, or it can go through AHB protocol or AXA protocol. So it doesn't matter. So as long as the designer knows how the protocol interface works, all they need to do is, with respect to simple approach, filling them in the write and read tasks. With respect to when they are using VIP, they need to fill up the bus to reg and reg to bus functions in the adapter sequence. So these are the steps which are used with respect to register testing using interface approach. This is the one which is simple approach, which is on the left-hand side in the previous slide. So here you generate the UVM reg model from IP-exact, generate a template UVM test bench through a tool script that may be available soon in the go to uvm.org. The skeleton UVM interface structure has a dummy driver and monitor that creates the write and read tasks. So fill in those write and read inside interface based on the DUTS configuration bus protocol interface. write the test, and it's easy plug and play. So we do have some code snippets. It will be available in the web later. So in this slide, I'm trying to mention about the usage of VIP BFM model with some UVM knowledge. If the designer knows how to handle the VIP, they can create, first two steps are similar, but the third step is where the skeleton UVM structure has an adapter sequence driver that calls the bus to reg and reg to bus functions. So when you are trying to write, you use this reg to bus, and then when you get the transaction back, this is the one which gives it back. So this is the UVM structure. And you can create the VIP transaction using the data type, fill in those functions, and that's it. Write a test in UVM framework. So this is the simple approach where you fill in the write and read tasks based on the configuration bus protocol. So there is a code snippet on how it can be used. So for example, if you have this is a simple protocol where there is a write, read, valid, and that's a control signal, and then you have the write, and then the data is the data bus. So you fill in those accordingly, and then at passage of clock, again, you reset the write, read, valid. So this shows a simple approach where you can fill this part very easily by a designer without need to know about UVM. And all they need to do is import this package and use these macros and fill in this based on their application configuration bus protocol interface. This is the read API, this is similar. And usage of VIP, if they have preliminary knowledge of UVM and how to use the VIP, they can extend the reg adapter and fill in these adapter functions, bus to reg and reg to bus. So reg to bus handles both UVM read and write initiation tasks, and then bus to reg handles the read. Basically, it returns the data back to the register. Here we just put a thin snippet of how a test looks like when they use these sequences underneath. Testing reset propagation by the designers, right? So there can be complex reset controller where a core has a subcores and they have their sub registers where they can do a soft reset or they can have a hard reset. Within each UVM reg block, there can be sub register blocks where they can do the reset. So how to test them upfront without the help of the DV framework? You can use the similar reset sequence, you can apply that. Initiate writes to the random registers within the reg block that you intend to apply to those sub blocks for the soft reset or reset. Apply the reset or soft reset to the intended blocks either through register write or through force deposit release methods using the APIs or macros, and then initiate the read back. Of course, this is traditional self-check, end of test. And you can have these APIs and macros which Srini told that can be available, or your own APIs or macros can also be used. You can also create control as system verilog assertions to ensure the reset propagation on into those sub blocks.